okay, got it. Oh, I see what's going on here. How about this? So the Success Center, and let me just, yeah, they keep changing the name. And I guess it doesn't matter. It used to be the Learning Center, and then it was like the Learning Success Center, and now it's just the Success Center. And but I just wanted to show you that I did post a link to the Success Center, which is free tutoring, right? And so really nice. They're already paid, so you don't have to worry about that. So it's now just a matter of using them because they are already there, right? And so, and maybe what I'll do is I'll move this down because that's my funny for later. How about the Success Center offers free tutoring for math, stats, biology, chemistry, physics, all of those. That's crazy. I'll highlight the free. Okay, so sorry, I guess I haven't really talked today. It feels like I'm like all right, so that was really good. And I guess he's not here. I was going to thank him for coming in, but anyways, so where we ended last day, I'm gonna have some water. My voice, that's all I do for work is I talk, blah, 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 blah. Can't have it cracking. Yikes. All right, so for some review, we finished by saying that, okay, so if we have a normal distribution, if we have a normal distribution, right? Technically, it would work for any symmetric distribution, but I'm going to specify that it should be normal. Then here in the center, we have the mean, but also the median, but also the mode, right? So if we have a normal distribution, then they are going to be the same, right? And then I've got this kind of funny. So I've used this one before, and I actually thought that these two people were the same. I still do. I still think that they're the same person, making it even funnier. So the problem with the mean is that the mean is always going to go in the direction of any extreme values. So in the direction of the tail, right? Whereas the median is just going to hold steady and be a good representation of the center of the data, right? So the mean is always pulled in the direction of the tail. So the tail is the outliers, right? And so the mean is always pulled in the direction of the tail, which would be outliers. Okay. Which means that if you have a distribution like this, right, then the median would be somewhere here, the median is roughly equal to the mode, and the mean is pulled in the outliers are amazing. I agree. Have you guys read the book Outliers? It's by Malcolm Gladwell, and it's really good. Anyways, it has to do with outliers, not in this sense, though. So here, if we have this sort of situation, then the median is kind of holding steady. The mean is pulled in the direction of the tail. Okay. So what we can do then is, sorry, if we have values for the mean and the median, then typically what we can do is we can just look at those values and have some general idea of what the distribution might look like. That's not necessarily what it's going to look like, but what it's likely going to look like, right? And so if we know the values of the mean and the median, we can develop a pretty good understanding of what the distribution would be, right? Is it going to be normal or is it going to be skewed? And if it's skewed, in which direction, right? We can develop a pretty good understanding. There are circumstances where if we have a bimodal distribution that's symmetric, that's a problem, right? Because then the median would be in the center, the modes, you'd have two modes, and the mean would be in the center because it's symmetric. So, but those rarely happen, right? And so that's why I say a pretty good understanding of the shape of the distribution. Yeah. Good. So that's kind of where we left off last day. So what I want to do is I just want to keep going through these notes. So where we left off here, right, is that how we define the median, where we want to say that it is not pulled in the direction of the outliers, is we call them resistant to outliers, right? Because they just kind of hold steady. And so we use the median and the interquartile range, which we're about to introduce here, for non-normal distributions because they are resistant to outliers, right? And then the mean and the standard deviation as well is not resistant to outliers, meaning it would be pulled towards those extreme values, right? And then here is what we summarized earlier. So if the mean and median are roughly the same, we can usually assume we have a normal distribution, right? Even without looking at the distribution. Good. I guess I mentioned it, so I can bring it into our notes, although it's being really slow. Okay. I'll highlight that resistant to outliers because that's how we summarize it. Okay, so the next thing we want to do is we want to find the interquartile range. Now the interquartile range, we need to go a little bit backwards. Okay, so Inter means between, and the quartiles are going to be values that split your data into quarters. Okay, and so here, let me bring this in here. Why is it taking forever? Here, put it on a fresh page. So if we have our data, right, and we've sorted them from smallest to largest, what we did to find the median was we found boop, 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 and we found the middle value, right? And so the median is what we call the second quartile, okay, Q2. So how we denote the quartiles is we use a capital Q, typically with a subscript 1, 2, or 3. Now, usually we don't talk about Q2 because it's called the median. So usually we talk about the median instead, but they're the same, okay? And so Q3 is going to be the third quartile. So what it's going to look like, if you want to think about a number line, from the minimum value to the maximum value, whatever they are, we said that, okay, in the middle here, right? So imagine you've sorted your data from smallest to largest, right? From the minimum to the maximum. And then the median is that middle value. Okay. It could be a middle value, or what we saw last day, right? If I land on 2 values at the same time in the middle, then the median is the average of those 2. So then here, this is the median, splits it in half, right? So now I have 50% below and of course 50% above. Okay. Whereas here, the first quartile, Q1, is essentially the median between the minimum and the median, right? It's the center value just focusing on that lower half, okay? Whereas the third quartile is the center value just focusing on the upper half. Okay, so let's see if I can find a different color here. Q3. So starting with Q1, what it looks like is, well, I've got a quarter, 1/4 below, which means I have 3/4 above, so 75%. Looking at Q3 then, well, that's the point that splits my lowest 75% of my data, or my lowest 3/4, from my largest 25% or 1/4, right? But it's just chopping up our data into quarters. Okay. Now this distance here between Q1 and Q3, this distance, this distance is what we call the interquartile range, the IQR. Okay. So how do we find the interquartile range? Well, Q1 is always going to be less than Q3, but we just need the distance. So to do that, what we're going to do is we're going to take Q3 minus Q1. So we'd find that the interquartile range is Q3 minus Q1 to find that distance. Okay. So if we have a skewed distribution, then what we use for our measure of spread, instead of the standard deviation, which only really works well for a normal distribution, if we have a skewed distribution, we use the interquartile range. Okay. So what we need to do is we need to be able to find these quartiles, but we already kind of said it, right? It's basically finding the median once we've found the median. So first we find the median overall, and then we focus on the lower half and we find the median there. And then we focus on the upper half and we find the median there. And those new medians are actually the quartiles, right? These are, so the quartiles are special cases of percentiles, okay? Oops, okay, I'll just keep it in. Let it think about it for a bit here, okay. There. So the quartiles are special cases of the percentiles. Now the percentile, the pth percentile, has p% below it and 100 minus p% above it, right? And so the 25th percentile would be Q1, right? Because it has 25% of the data below it and 100 minus 25, 75% above it, right? So they're just special cases of the percentiles. So how we find the quartiles, okay, is similar to finding the median, okay? But remember, there were two different ways that we would find the median. The first way is if we land on one data point, right? Then that data point has already been used. So it's been used, so we can't use it again, okay? Whereas if we took the average of two values, so if we landed on two values at the same time, then we work out from the line that we drew in the center, okay? Let me see what I have in here because I can't quite remember. But what I want to do is I just want to show you what I mean. So I'm going to grab this. Does this have 12 data points? 1, 2, 3, 4, 5. I guess I'll find out here. So I am just going to make sure that I have 12 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, good. So what I'm going to do is I'm actually going to remove this, but I'm going to write these all out across the page so that it's easier to see, right? So let's see here. 2.9, 3.2, 3.9, 4.1, 4.4. Notice that these are sorted, right? That's the most important first step. 4.7, 5.2, 5.4, 6.2, 7.3, and 9.4. Just to double check, make sure that I have everything, otherwise everything would be all wrong that I'm about to do. So I need to make sure that I have 12 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Phew. So I'm going to delete that. Okay. So here I have 12 data points. Okay. Then what I want to do is I want to copy all of these, and for the 11 data points to show you the other scenario, I'm going to remove the 9.4. Okay. So down below here, I'm going to have 11 data points. Right? Remove the 9.4. And I'm going to cheat a little bit here so I don't have to write these all out again. Just going to copy and paste. Okay, maybe make a little bit of room here. How about that? Okay, so where we're going to start, and maybe I'll bump these down a little bit. Make sure I have some room here. We're going to review and we're going to find the median of each of these, right? But we have them already. And so I'm just going to boop, 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 boop. So I landed on two values at the same time, 4.6 and 4.7. And I'm just going to double check that my eyes didn't play tricks on me, but I'm pretty sure 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, good. Has to be the middle value, right? So you should have symmetry around your median. So now what we do when we land on two values at the same time, we're going to draw a line down the center here to indicate that that's where the median is. And then the median is going to be the average of those two values, right? So the median is 4.6 plus 4.7 divided by 2, which is 4.65. And I'm going to bump this down because I clearly need more room. And I'll probably end up bumping it down again. But I just wanted to have it all. Okay, so when okay, I'm sure I have it outlined in the text, but I'll just talk about it. So when the median is here at this line, so neither of these values are the median, right? So the median is at that line. So then where you start counting in is from the 4.6 and the minimum, okay? So here, you would start here, 1, 2, 1, 2, okay? And we're gonna have that I landed on these two values at the same time, right? So now Q1 here is going to be the average of these two values, 3.9 plus 4.1 divided by 2. And I just don't trust myself. 3.9 plus 4.1 divided by 2, phew, okay, is just an even 4. Yeah. Same thing on the other end. So because the median is here at this line, that's why I can use this 4.7. Okay, later in the next example, what we'll see is we'll land on one value. But once we've used that value as the median, we can't use it anymore. Okay, so notice how the numbers that you get would be different, right? So you want to make sure that you've got this all under control. So here, I'm going to go 1, 2, 1, 2. It's going to be the same scenario because, and I guess I should use the same colors here. Orange. Orange, you glad I didn't say banana. I'll draw a line down here to show that Q3 then is 5.4 plus 6.2 divided by 2. Let me just confirm. 5.4 plus 6.2 divided by 2 is 5.8. Okay. So now we have the first quartile, we have the median, which is the second quartile, and then we have the third quartile. And wrapping all that data up, we have the minimum and the maximum. So what we call that list of 5 numbers from the minimum. Okay, so I'll go here. This is our minimum, of course, because we've sorted the data from smallest to largest. So then here, this is our maximum. This is what we call a 5-number summary. The minimum, the first quartile, the median, the third quartile, and then the maximum. That's our 5-number summary. We call this our 5-number summary. The minimum, Q1, median, Q3, maximum, right? That's our 5-number summary. So usually what happens is I just end up asking for the 5-number summary. So I give you a list of values and then you have to find the 5-number summary. So it's going to be really important that you know how to find the median, the quartiles, and of course the minimum and the maximum. Those are easy, usually, unless you've forgotten to write out a value. then you're hooped. Okay. So just for practice, let's do this next one. Okay. So what happens is when I count in, starting at 7.3 and 2.9, boop, 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 boop. So I actually end up here on 4.6, which means that the median is 4.6. So now when I go to find my quartiles, right, my first quartile down here and my third quartile up here, I cannot use the 4.6 anymore. So where I start my booping here is at 4.4, 1, 2, 2. So then my Q1 is the 3.9. Same thing over here. Because I've used 4.6, I cannot use it again, so I have to start here at 4.7. Boop, 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 boop. So in this case, I land on 5.4, so my Q3 is 5.4. And now, of course, in this case, my minimum is still 2.9, but my maximum is 7.3 in this case. Okay, so those are the two different ways that we can find, or that we have to be comfortable with to find the quartiles by hand. If you end up using something like Excel, Excel does like a weird adjustment. It's not weird, it's more sophisticated than what we're doing. But if I give you a list of values, I am assuming that you're just doing it by hand. So if you end up using Excel, then you might get the wrong values. So, and this is something that I will ask you to do. So just know the rules that we just talked about here. Okay. So here are all those instructions that we just talked about, right? So we can try to confirm our results with R, right? But R is more sophisticated than our method, so we'll often get slightly different values, okay? So the quantile command gives us the quartiles. I know that sounds weird, but that's just how they decided to do it. So let me bring that in here. Okay. So here, GDP is that data set with 12 data points, right? So if we do a comparison here of our values, right? So our minimum is 2.9. We found our first quartile to be 4, okay? And I think they found it to be 4.05. So notice how these are different. So, and I think the 5.6 is also different. So these differ because R uses more sophisticated methods. Where it just kind of uses a little weighting game, and because we took the average of the central two values, then it looks, and so this is more sophisticated. This is not the result I would be looking for. I would be looking for the first result that we found. Okay. unless I tell you to use R to find it, then of course I would be looking for this here. Notice that the quantile output goes from 0%, which is our minimum, 25% Q1, 50% median, 75% Q3, 100% maximum, right? So that is a 5-number summary. And if we compare just the one with the 11 points, our values are, again, I think slightly different. Okay. If we wanted to find a different percentile, right? So pth percentile, not just the quartiles, right? Which are a special case of the percentiles. If we wanted to find something like the 15th and the 25th and the 35th percentiles, let's say we have a list of percentiles that we want, you could just do one. But usually we give it a list of things that we want. Then what you would do is you would specify this probability command. Okay, so prob equals, and if you have a list of things, then you would wrap them up in a C, right? So here, use the concatenate to enter a list of values. And that's pretty common that we use it that way. Okay. But the prob command, if you just said the quantile of GDP prob equals 0.45, it would just give you one percentile, the 45th percentile. Okay. Good. So that's a little bit new, right? But once you kind of dissect it and you kind of make the connection of what we entered here and what the output is, then it's not so bad, right? We're just adding an argument, it's called, to this command. Okay, so there's the default arguments, which is the quartiles, and then now we can alter the arguments. Adding an argument to the quantile command. Good. So just something to play around with. So the 5-number summary, we mentioned it. It's a list of the minimum, the first quartile, the median, the third quartile, followed by the maximum. Okay. And it has to be in that order. So either ascending, so going from minimum to maximum, or from maximum to minimum, but that feels weird, right? Usually we go from minimum to maximum. So I always go from minimum to maximum, but it has to be in order. Must follow this order, right? Sometimes people like to give me the values as we find them. So typically what we do is we start, and the first thing that we find is the median, right? Because we need the median to be able to find the quartiles. So then they give me the median, and then you find the first quartile, and then you find the third quartile. So you jot those down, and then you finish off with the easiest ones, the minimum and the maximum. But in that order, that means nothing, right? So it has to be in order. So often what I'm going to do is just give you a set of numbers and ask for the 5-number summary, which includes finding the median and finding the quartiles. Right. And so in R, we can use the summary command. The summary command gives us the And let's see if I can copy here. So slow. I'm going to pretend it's on the same page. So now, right, when we have this summary command, oops, here, notice that it gives us the minimum, the first quartile, the median, and the mean, which is not part of our 5-number summary, but we started off the class today saying, okay, well, if we have values for the mean and the median, that's going to give us a clue as to what this distribution might look like, right? And so that's really useful information. And then we finish off with the third quartile and the maximum, right? And so here, notice that this is not part of the 5-number summary, not part of the 5-number summary, but useful for comparing to the median. Okay. What can we do here? We can look at 4.65 versus 5.108. Is this, I'm not sure what you mean by ungrounded. Do you mean kind of an infinite data set? It only applies to samples, and samples are finite, if that means. So ungrouped. Not necessarily. You don't have to have ungrouped data. You could have groups, but then you would be comparing this 5-number summary of each group. So I would say you can look at the 5-number summary for anything. So it could be the entire sample, or if you've got the sample is grouped, then you could look at the 5-number summaries and compare those 5-number summaries between the groups to gather information that way. And I think that's what the question was. Okay. I'll wait for a correction if I was wrong. But anyways, so here, right, these are relatively similar values at 4.65 and 5.108. If I had to guess, right, then the tail would probably be going a little bit further into the right, because the mean is larger than the median. So if I had to guess what this distribution might look like, it might look something like this, right? Where we have the median would be here, and then the mean would maybe be pulled in the direction of that tail, right? Little bit of a tail here. Yeah, so I would call it approximately normal, right? Because that's what we're always pushing for. So in this case, I would try to argue that, well, these values are roughly the same, so we have an approximately normal distribution, right? This is such a small data set that this sort of difference is not going to be a big deal, right? It would even out as we collected more data. So good. So especially for larger data sets, if you have the mean and the median are similar, then you likely have a normal distribution. At least you have a symmetric distribution. Right? Okay, good. So let's see here. the next thing I want to talk about is, are there any outliers? Now, the outliers, usually you can look at a data set and you can have a pretty good idea of what will be an outlier. But what happens is we can't just say, oh, I think this is an outlier. Instead, we need to have some sort of way to say, because this point is larger or smaller than this, that's why we consider them an outlier. And so we're going to use what's called the 1.5 IQR rule to find outliers. Now, remember the IQR is the distance between the Q3 and Q1, or Q1 and Q3. There are tests that we can run to say if it's approximately normal, but for now, just looking at the histogram is going to be good enough for now. And then comparing the mean and the median would also be another thing. So there's no threshold value, there's no threshold difference that we could look at. But there are tests that we could run, but we haven't introduced hypothesis testing yet. So, but maybe what I'll do is I'll bring in an example to show you another test later on, but that's going to have to be way later in the course. We're not there yet. Okay, awesome. So remember, the interquartile range is the distance between the first and the third quartile. And so there are many rules. We use, I think it was Tukey that introduced, and he's a famous statistician. He decided that 1.5, that's a good trade-off. We're still able to identify outliers, but we're not saying that too much of our data is considered an outlier. So again, there are many other rules that we could use, but this one is the most common. Okay, so the 1.5 IQR rule says that any values that are beyond a lower or an upper bound will be considered outliers, right? So imagine on your number line, right? Is it possible to predetermine our outliers looking at the skewness of the distribution? So the outliers would be in the tails, so towards the skew, but we need some sort of mathematical way to determine that because it passed this point, right, that would be an outlier. So in case it helps, right, what if we have a number line here, okay? And we've got some data points, and maybe those data points are kind of here, 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 and here, right? And maybe that one's not there. What we need and what we're developing is that, okay, if a value passes this point or this point, then they would be considered an outlier, right? So here, this would be the lower bound. So any values that are smaller than the lower bound would be considered an outlier, whereas here, this would be our upper bound. And any values beyond that point would be considered an outlier. And so here in this case, right, that would make this an outlier, because it's past that upper bound. Okay, so to find those bounds, what we do is we say, okay, a distance of 1.5 times the interquartile range down from Q1, okay? And then for the upper bound, we move up from Q3, we move a distance of 1.5 times the interquartile range. Notice that here, it gets a little bit confusing, right? Because we have Q1 minus 1.5 times the interquartile range, and then Q3 plus 1.5 times the interquartile range. But if we remember the quartiles, right? then we need to move down from Q1 and we need to move up from Q3. And so that's why we have that minus plus situation. Okay. Oh, grab the wrong thing here. So here, let me wait for it to copy. And I think I copied too much. Yeah. So here, if we look at our data set with 12 points, right, we suspect that 9.4 might be an outlier, right? And so we can calculate the lower and the upper bounds to determine if there are any outliers. Okay, so here, the interquartile range is Q3 minus Q1. So that means that the interquartile range in that case for that data with the 12 data points is 5.8 minus 4, which means the interquartile range is 1.8. So now we can go ahead and find the lower bound, which is moving from Q1 down 1.5 times the interquartile range, which is a distance of 2.7. So the lower bound here is 1.3. So what I want to do is I want to show you that data set here, because we worked it out already. I'm going to copy, and I am going to shrink it up a little bit. Copy. Okay. To have it beside here. Okay. So what we're doing is we're taking this distance, right, between 5.8 or 4 and 5.8 is 1.8. And then we're multiplying that distance by 1.5. And then we're going from Q1. I want to move down a distance of 2.7, which is 1.5 times the interquartile range, which puts me at a lower bound of 1.3, right? 1.3, which means that any value less than 1.3 would be considered an outlier, right? But if I draw 1.3 on this sort of number line because they're sorted, then I can see that there are no outliers on the lower end, right? So since there are no values smaller than 1.3 in our data set, right, the minimum is 2.9, there are no outliers on the lower end. Okay, so I like to have the values sorted out like this, because then I can just put 1.3 where it would fit in, right? And same thing if I go ahead and I find the upper bound, which is going to be from Q3, now I'm going to move up 1.5 times the interquartile range to see where I land. Now notice that here the upper bound is 8.5, which in terms of the number line would go somewhere here, right? 8.5. Okay, which means that 7.3 is inside the bound, so it would not be considered an outlier. However, 9.4 is outside that upper bound, and so it would be considered an outlier. So since there's one value, that value is 9.4, beyond the upper bound, there is an outlier in the upper end. So therefore, there's one outlier in total. Okay. So, good. So that's how we use this, the data kind of sorted out like this. We find the 5-number summary, but then we can also look at the lower and the upper bounds to figure out if we have any outliers. Okay. We can do the same thing for the data set with 11 data points. But what I want to show you is that we can visualize this relationship. So the 5-number summary and the lower bounds and the upper bounds and the outliers, we can visualize it using a box plot. Okay. So the last thing I want to show you for this is making a box plot. And I also want to show you what a box plot looks like, because it's going to help us figure out what we need to do here. So I'm going to bring here here we go. Okay. So here, all it says down here is that notice that R uses the y-axis for the scale. You could flip it and have it just kind of on a number line. That's fine too. But notice that the box plot, well, it's got some key components such as a box in the middle. Okay. And so what happens is that we draw the median. Oh. The median is this kind of thicker line in the center of the box. Okay. Whereas here, this is our Q1. And this is a line at Q3. Okay. These are kind of cute. They're called the whiskers. And this is the whisker as well. And then let me see if I can find a red maybe. Okay. Make sure it looks okay. Okay. So what happens is that the whisker is the hardest part. So when we're drawing these, or when you're looking at these rather, then the whisker is going to be drawn at the smallest, or the largest data point on the upper end within the upper bound. Okay. And so it goes to the data point that kind of maxes out within the upper bound. So in this case, this would be at 2.9, and this would be at what, 7 point, I feel like it's 7.3, right? So the upper bound went to 8.5, but the line is drawn at 7.3, right? The lower bound is at 1.3, but the whisker is drawn at 2.9. Okay, so that's kind of going to be important, because this is at 2.9 and that's at 7.3. So how I like to do it, if I have to do these by hand, and I might get you to do it because it's a good exercise in, I don't know, following instructions, I guess. Isn't that all of school? It is. So here, right, what we do is I tend to temporarily draw a line at the lower bound, which was 8.5, or sorry, the upper bound. Let's start there because I'm working here on the upper end. So here, what I would do is at 8.5, I would temporarily draw a line there. There's no data at 8.5, right? The lowest possible, or sorry, the largest possible data point was at 7.3. So that's why I temporarily draw a whisker to the bounds, and then I bump it down into the actual data. Okay, so I'm going to remove this here because I don't want it to be confusing. And I've got the instructions here. So to make a box plot, well, I'll let it resize here. Okay. It's really just a visualization of the 5-number summary, right? Including if there are any outliers, and it uses the 1.5 IQR rule. So first, you're going to have to determine the appropriate axes. So that depends on what your data is on, right? And it depends on what you're talking about, right? And so in this case, you look at the data and you look at your minimum and your maximum, and we decided that a scale from, I don't know, I guess 2 something to 10 seems appropriate. If you wanted to, you could go all the way to 0, but there's nothing happening there, so we didn't in this case. I just tend to stick to the default settings in R. So what you do is you're going to draw lines at the median, right? And that's this thick center line, okay? And then you're going to draw another line at the first quartile and the third quartile, right? So you start here in the middle, you start and you draw your median, and then you draw your first quartile and your third quartile, okay? Then you're going to connect the lines of the quartiles to make a box. Right, so that's how we get this box, is we connect the first and the third quartiles. So far, so good. Then you're going to temporarily draw lines at the lower and the upper bound from the 1.5 IQR rule. Okay. Then you're going to extend the lower whisker to the smallest value inside the lower bound and indicate any outliers by a star. Okay, I think here it uses an open dot. Sometimes it's a star, sometimes it's an open dot, but we can see what it means, right? So if you want to use a star or a dot, that's fine. Then you're going to extend the upper whisker to the largest value inside the upper bound, and then indicate any outliers by a star. Okay. So notice how making this box plot requires that you know a lot of information, right? And so it's not because, so I don't ask you to make a box plot because it's important for us to be able to draw a box plot. No, the reason I make you draw a box plot is so that I can ask you one question that makes you find the median, the quartiles, identify any outliers by finding the upper and the lower bounds, right? So it's kind of the total package in terms of a question, but it's not important to be able to draw a box plot. We have software for that, right? But it is kind of a good question that asks you to find a lot of things, right? Or requires you to find a lot of things. Okay. So let's see here. Okay, so that's kind of where we're going to leave numerical data for now, right? So I just want to talk about visualizing and summarizing categorical data. Categorical data, right, is a little bit different because now we don't have numbers that we can work with necessarily. We're just going to have counts in each category. Okay. And so in general, I'm just going to bring in let me see here. So if we have categorical data, to visualize categorical data, we're going to use bar graphs or bar plots or bar charts. Graphs are, just as a side note, a graph is a plot, which is a chart. Okay, so you can call them bar graphs, bar plots, bar charts, pie graphs, pie plots. That's weird. Right, and so we have a couple of options for showing counts in each category, right? So now to visualize categorical data, which means we have counts for each category, right? How many people have blonde hair? How many people have brown hair, or I guess it's auburn or whatever? How many people have black hair, right? And how many people have crazy colored hair? I'm not that cool, right? And so right? Those would be categories, the hair color, and then we would have counts in each category. So to represent those and to easily kind of gather information, then we use what we call a bar graph. And the bar, the height of each bar is just going to be the count, right? So you've probably seen pie charts or pie graphs, or if you've played around in Excel, then you've probably seen donut charts. I do not like pie charts or donut charts, and I will kind of expand on why, right? But although pie charts are popular data visualizations, we should only use bar graphs for visualizing categorical data, okay? And the reason is that we should use bar graphs because even small differences are detectable, okay? So instead of introducing the data set, which I'll leave for next day, which I guess is tomorrow, yikes, okay. Instead of introducing this data set, which is just a cars data set, I'm going to try not to introduce it, but here I go, okay. Instead, I just want to show you the difference between these two. Wait. Hey. Okay. So I'm just going to bring this in, and just without even knowing what the data is, I mean, you have probably had a chance to read that summary by now, right? But the reason that I will only talk about bar graphs, so I do introduce pie charts, but only to tell you, do not use pie charts, right? And so if I asked you to look at this, so this is the same data here, and I asked you which slice is the largest, right? You could, if you spent some time, you could figure out that the 8 slice is the largest, right? And then followed by the 4 slice, and then followed by the 6 slice. But it takes some work, right? And so you need to remember the key thing about data visualization is that we need it to be just kind of instant, right? We shouldn't have to spend a lot of time looking at it to gather information, right? Whereas here, when I'm looking at these bars, it's very obvious to me visually that the 8 bar is the tallest, right? And so here it's way easier to see these differences, even if they're small differences, okay? So that's why we should use bar graphs instead of pie charts. And I guess, so a lot of work has been done on the human brain, of course, and I guess the human brain has a hard time assessing area, right? And so we're good at seeing the different heights, right? So we can look at this and our brains are quick to pick out the tallest one, the shortest one, right? Whereas here, when we have to assess the area, it's really hard for our brains to do that, okay? And so that's why we should not use a pie chart. And I've got kind of a funny here that I'll try to show you guys with the remaining time. But first I'll bring this in here. So in the pie chart, it's not clear which one is the largest, right? But here it is. So we should always use bar charts instead of pie charts. If you think about it, the only time a pie chart is obvious is when there are only 2 categories, right? For example, let's assume just for a second that we have just two genders, because that's kind of a classic example. And so it just simplifies things. But so let's say we have males and females, right? Then knowing the count in the male group tells us that, okay, well, out of 200 people, if I know that there were 40 males, then I also know that there were 160 females, right? And especially in terms of percentages, if I tell you that 20% were males, then we know that 80% must be females, right? And so we actually only need one number for that. And so I'll bring this in as well as the little example on the side. Okay. So let me bring this in here. Come on. So here, right, if we have just two categories, right, then knowing the count in one or the percentage means that we have the count in the other or the percentage in the other, right? And so we don't need to visualize that, right? Because then the same information could be conveyed with just one number, and that's the simplest way to do it, right? So the percentage who agreed with a statement in a sample was 43%, implies that the percentage who disagreed with a statement in the sample was 57%, right? The opposite of that. And so I don't know if you guys watch Superstore, and I'm going to try and see if I can share it, or maybe the sound is going to be weird. But what I did was, so they're talking about people who smoke marijuana. And so I'm going to see if it plays. But this is a clip from Superstore, and I think it's really, really funny.
Really be surrounded by killers? You don't think people in this store do marijuana, do you? I mean,
probably.
wait, how many of them?
Like half.
Half? Wait, half do or half don't?
It's both.
Oh no, it's glitching out. Anyways, I'll see if I can post that because I think it's really funny. Because I fear it was glitching out there. But so he goes, half do or half don't. And so Amy says, both? Both? So he gets all upset. So anyways, I'll try to post that little video there because it's really funny. And so that's something to think about. And so that's what I want you to think about. If you catch yourself making a pie chart of half do and half don't, well, you don't need to do that, right? You just need to say that half do, and then it's implied that half don't, right? And so just kind of a funny example. In fact, yeah, Superstore is a really funny show, and they do make a lot of statistics jokes, just kind of basic statistics jokes. So I think it's funny for that reason as well. All right. Okay, so I think I'll save the rest of this for next day, just making tables and stuff like that. But I think that's a good introduction. So tomorrow we're going to finish this categorical data section because there's not a lot going on in there. If you have any questions, let me know. Otherwise, I'll see you tomorrow morning. Stop this.